But if 30% of the time you catch the train, you catch the bus the next day. Right? So on a particular day, you might go by train or you might go by bus, but the following day, the chance of you going by train is going to be 0.7. The following day, the chance of you going by bus is 0.3. There's really no advantage to go by between going by train and going by bus. It's just sometimes you choose to go by train and sometimes you choose to go by bus. If you choose to go by bus, then you might choose the next day to either go by train or by bus. Now, if you go by bus, the next day you might choose to go by train 20% of the time, and you might choose to go by bus 80% of the time. Alright? So far so good? So this is a tree diagram. Now, every time you catch the train, the chance of you catching the train the next day is going to be the same probability. So if I extend my tree diagram here, having caught the train on this day, my chance of catching the train the next day is 0.7. My chance of catching the bus the next day is 0.3. Having caught the train on this day, the chance of catching the train the next day is 0.7. The chance of catching the bus is 0.3. So every time you catch the train, the chance that you catch the train the next day is 0.7. The chance that you catch the bus the next day is 0.3. Every time you catch the bus, the chance of you catching the train the next day is 0.2. And the chance of you catching the train the next day is 0.8. So this is train, bus. And here we go. I've caught the bus, so the chance of catching the train the next day is 0.2. The chance of catching the bus the next day is 0.8. Okay? So that's a tree diagram. The tree diagram, as you can imagine, can get quite complicated because, you know, by the time I put in the next branch, 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 you know, like I've run out of room already. Okay? But the probabilities remain the same. If I caught the train, the chance of catching the train the next day is 0.7. The chance of catching the bus the next day is 0.3. If I caught the bus, the chance of catching the train the next day is 0.2. The chance of catching the bus the next day is 0.8. So this is constantly happening. The next day, the probability of me catching the train, assuming I caught the train that day, is 0.7. Bus 0.3. Here, 0.7, 0.3. Here, the next branch would be 0.7.3. Here, the next branch would be 0.7.3. Same thing with my bus branches. My bus branches are always going to be 0.2 and 0.8. Here, 0.2 and 0.8. Here, 0.2, 0.8, 0.2, 0.8. So the probabilities are going to be repeating over and over again. Okay? Now, what we can do instead of having a tree diagram to represent this, we could represent this using a transition diagram. Now, the word transition, what does that mean? Change. So we are changing from one day to the next how we're travelling to work or travelling to school or whatever, and we're going to represent that as a transition diagram. So if I travel to school by train, which I'm going to put in a circle, right? The chance of me travelling to school by train again the next day, so I travel by train, I'm going to travel by train again, that chance according to this is 0.7. Okay? However, if I travel by train, the chance of me travelling by bus the next day is 0.3. Okay with that? So those are the two things that I can do. If I travel by train, I can travel by train again, or I can travel by bus. Can you see how that transition diagram's gotten built up? Okay? However, the bus situation is slightly different, because if I travelled by bus, the chance of me travelling by bus again is 0.8. And the chance of me travelling by train the next day is 0.2. So that's called a transition diagram. So if I go train and catch the train again the next day, 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 it's always 0.7. If I go train and catch the bus the next day, then having caught the bus, I can either catch the bus the next day, catch the bus again, catch the bus again, catch the bus again, so I'll go around in that loop, or the next day I can catch the train. Now that I've caught the train, I can either catch the train again, catch the train again, catch the train again, or I can catch the bus. Having caught the bus, I can catch the bus again, catch the bus again, catch the bus again, or catch the train. Transition diagram, nice and neat. Okay?
Why would we draw that at the start instead of those? It's so much easier.
It's so much easier, isn't it? Okay. One of the things that a transition diagram doesn't do is it doesn't answer the question of, for example, what is the chance that in a particular week I caught the bus to school all 5 days? So the transition diagram doesn't actually answer that. A tree diagram can answer that, because if I'm talking about catching the bus to school on 5 days in a row, I could actually make a tree diagram with 5 sets of branches. So this is day 1, day 2, day 3 will be another set of branches, day 4, day 5. Becomes quite complicated. Okay? Or we could actually set up the next representation of this, which is called a transition matrix. So, in this particular situation, catching a bus or catching a train, okay, I'm going to set up, there's 2 scenarios, train or bus, and having caught the train, there's 2 more scenarios, train or bus. So does it make sense that we're going to have train and bus, and train and bus, we're going to end up with a 2 by 2 matrix, because there's 2 scenarios leading to another 2 scenarios, giving us our 2 by 2 matrix. Okay? So if I catch the train, this is my initial state, catching the train, what is the chance that I'm going to catch the train again the next day? It's 0.7. If I catch the train, what is the chance that I'm going to catch, if I catch the train, what is the chance I'm going to catch the bus the next day? 0.3. If I catch the bus, what is the chance that I'm going to catch the train the next day? 0.2. And if I catch the bus, what is the chance that I'm going to catch the bus the next day is 0.8. There's a couple of things to notice about a transition matrix. What does this column add up to?
1.
1.0. What does this column add up to? 1.0. In probabilities, our probability will always add up to 1, won't it? So if I'm talking about the train-bus situation, the probability of catching the train versus the probability of catching the bus, that adds up to 1. Here, the probability of catching the train versus the probability of catching the bus, that adds up to 1. So these 2 numbers, train and onwards, becomes my first column of my transition matrix. These 2 numbers, bus and onwards, becomes the second column of my transition matrix. Okay? So this is what's happening on a particular day. Probability of having caught the train, that I catch the train again, 0.7. Probability of having caught the train, I catch the bus, 0.3. Having caught the bus, I catch the train the next day, 0.2. Having caught the bus, I catch the bus the next day, 0.8. This transition matrix is called our initial state matrix. So herein lies the question. If I wanted to find the probability of catching the train every single day for 5 days, then what I'm going to do is I'm going to multiply that initial state matrix by itself 5 times. So basically what I'm going to do is I'm going to have this matrix, this 0, 0.2, 0.3, 0.8 matrix, and I'm going to multiply it by itself, and then by itself, and then by itself, and then by itself. And the answer to that multiplication that ends up in this particular cell here is going to be the probability of catching a train 5 days in a row. So having caught the train, then catching the train again, and train again, and train again, and train again, and train again, will be in that cell there. This cell here would be having caught the bus, what would be the probability of catching the train, and the train, and the train, and the train, and the train. This one here would be having caught the train, what's the probability of them catching the bus, and 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 the bus. And this one here would be what's the probability of catching the bus every day for 5 days. Okay, so the transition matrix, when we multiply by itself, enables us to answer questions like, what is the probability of something happening a number of times in a row? The good news is, you are not expected to have to multiply that by hand. What you are expected to be able to do is to set up a transition matrix like this from a set of information which is given in the question, and then do something like, if I call this matrix here my T matrix, my transition matrix. Okay, so this is my transition matrix. If I wanted to find out what was happening over a period of 5 days, I would raise that to the power of 5 using my CAS calculator, which is handily built for this task, and that would give me an end state matrix which indicates what each of those probabilities would be. Okay? So, what are you expected to be able to do about this? You're expected to be able to take a problem like a worded problem, like commuters are travelling into the centre of a town either using the bus or the train. Research shows that each month 20% of those, I said by day, this is actually 1 month, that each month 20% of those using the bus switch to train travel and 30% of those using the train switch to bus travel. Right? And if at the beginning of January 4,800 people use the bus and 3,600 were using the train, calculate the number, blah, 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 blah. Okay, so you're expected to be able to take a question like that. Good. Okay, and you're expected to be able to turn that into a matrix or a transition diagram, or both, and then use that to solve a problem like this. Okay? The other thing you're expected to be able to do, if you're given a transition diagram like this, you're expected to be able to turn that into a transition matrix. But we'll talk more about that later. The main thing that I want to get out of today is to be able to do, is to be able to get to the stage of writing the transition matrices. Now, the best way to do that is to do lots of practice.